So, welcome to lecture number 39 of our course on fundamentals of transport processes. As you recall, in the last lecture we were discussing turbulent flows. Many characteristics of turbulent flows. One is they are primarily at high Reynolds number, because you require the nonlinear terms in the equation to have multiple solutions for the conservation equations. As I said, even at high Reynolds numbers, the laminar flow is still a valid solution of the equations of motion. The only problem is that the laminar flow is unstable. At low Reynolds number, the laminar flow is stable, which means that if I have a flow and if I put in a small disturbance, that disturbance decays, it damps out, and you get back the laminar flow as time progresses. Whereas, as the Reynolds number increases, there comes a transition Reynolds number, which depends upon the flow configuration, for which if you put in a disturbance, that disturbance does not decay, but amplifies. In other words, any spontaneous disturbance, and in nature there are always disturbances in nature. If you have a pipe flowing, there is always some sound wave, some vibration, something or the other, which will act as a disturbance for the velocity profile. That disturbance will spontaneously take the flow from the laminar state. It will spontaneously grow because the flow is unstable, and it will take the disturbance, the flow from the laminar state to a turbulent state, a highly irregular chaotic state, only at high Reynolds numbers, with large velocity fluctuations. So, even though the flow is statistically steady, that is in the limit as time progresses, if you take an average over time, if your period of averaging is larger than the frequency of the fluctuations, those averages will be independent of time. However, at a given location, there will be a fluctuation in the velocity profile in all components of the velocity as a function of time. And this irregularity is a characteristic feature of the turbulent flow. In other words, the fluctuations are not regular in the sense of being periodic oscillations with one particular frequency, but rather they are chaotic, they are highly irregular oscillations which do not have a well defined frequency characterizing them. They are three dimensional. So, even though I may have a two dimensional flow, for example, the flow in a channel is a two dimensional flow in which the mean velocity is only in the flow direction along the walls, whereas the velocity gradient is only perpendicular to the walls. Even though the mean velocity may be two dimensional, the fluctuating velocity is in general completely three dimensional. At each location you have velocities in all three directions, and these are fluctuating velocities. In the flow direction there will be a mean velocity, in the other two directions the average of the fluctuating velocities will be 0, but the fluctuating velocities themselves will be non-zero nevertheless. Because of these velocity fluctuations, the amount of energy that is dissipated is much larger than what you expect for a laminar flow with nice straight streamlines, because you have these additional fluctuations which cause additional strain rate locally and additional dissipation, due to which it is a highly dissipative flow. And also the diffusion of mass, momentum and energy takes place not primarily not due to molecular diffusion, but rather due to the motion of these eddies, which are correlated parcels of fluid of various length scale, which are transported across the fluid, resulting in an enhanced transport of mass, momentum and energy. For this reason, they are highly diffusive and also highly dissipative, because the momentum transport rate is much larger than what you expect for a laminar flow. And for that reason, the flows, the friction factor, for example, in a pipe or a channel turbulent flow is much larger, sometimes orders of magnitude larger than that in a laminar flow. Okay. So, last class we were trying to look at how we would analyze this highly fluctuating velocity profile. As I said, one way to analyze it is to separate the velocity into a mean velocity plus a velocity fluctuation. and then try and obtain equations for the mean velocity alone. If you could obtain an equation for the mean velocity alone, then one could solve that equation and find out the velocity profile throughout the flow. As we saw in the last lecture, it is not possible to obtain an equation for the mean velocity alone, because when you write an equation for the you take the momentum conservation equation and average it over time, you do get terms which depend upon the velocity fluctuations. That is because, as I said, there is momentum transport taking place due to velocity fluctuations, and that inevitably has to come into the momentum conservation equation. Then we went and looked at how is the energy in the flow produced, that is, at the large scales what produces the flow energy, and how is that energy dissipated. And that led us to the discussion of the smallest scales in the flow, the microscales. So, let us briefly review that and then progress with how we would go about modeling these turbulent flows. As I discussed in the last lecture, turbulence is a continuum phenomenon. It is not, it does not, when the flow becomes turbulent, it does not mean that the continuum approximation is breaking down. The equations of motion are still the continuum Navier-Stokes equations. The solutions are such that the velocity is highly irregular. Okay. So, the starting equations are, as usual, the Navier-Stokes mass, moment and momentum equations. The Navier-Stokes mass and momentum equations, and since the velocity is a fluctuating function of time, the velocity has some fluctuating function of time, an irregular fluctuating function, we can separate it out into a time averaged mean velocity. Okay. This is the time averaged mean velocity, which I call with as capital U. Okay. The time averaged mean velocity, which I call as capital U, plus the fluctuating velocity. Okay. So, the mean velocity is defined as 1 over t integral 0 to t dt of u vector. Okay. It is averaged over a time period which is long compared to the largest time scale of the velocity fluctuations. Usually, the largest time scale of the velocity fluctuations will correspond to the mean strain rate, okay, at that location. And for our present argument discussion, we are only looking at steady flows, that is, there is no time dependence of the velocity profile. Okay. So, we just look at only steady flows. The fluctuating part is the local instantaneous fluid velocity minus the mean velocity capital U. Okay. And since it is the instantaneous velocity minus the mean velocity, okay, it implies that the average of u prime, which is 1 over t integral 0 to t dt of u minus u, this is equal to 0. The average of the fluctuating velocity has to be equal to 0, okay, because I have already subtracted out the mean velocity. So, this fluctuating velocity has a 0 average, okay, and one would hope that I can derive an equation for the mean velocity alone by taking an average of the entire mass conservation equation after substituting for the velocity and the pressure as the sum of the mean plus the fluctuating part. Okay. So, I substitute u is equal to capital U plus u prime vector into the mass conservation equation, okay, and then I write down the entire equation. Okay. So, in the last lecture I had written this explicitly as del dot tau vector, where tau was the shear stress. Okay. You can do either one of the two, you can take either the stress or the velocity gradient explicitly. Okay. So, when we wrote this, when we substituted this and took the average, we got an equation of the form rho times u dot grad u is equal to minus grad p plus del dot tau plus the divergence of a second term. Okay. Or if I write it in indicial notation, you will get rho u j partial u I by partial x j is equal to minus partial p by partial xi plus partial by partial xj of tau ij plus partial by partial xj of t ij. This second term is what is called the Reynolds stress. This is because of the velocity fluctuations. Okay. The Reynolds stress, as you recall, can be written as minus rho times the average of ui prime uj prime. Okay. As I said, the average of the velocity itself, just for completeness, I should also say that the pressure is written as the mean pressure plus the fluctuating part of the pressure. Okay. Just for completeness, the pressure is written as a sum of a mean plus a fluctuating part. Okay. And when I take the average of the entire momentum conservation equation, I have the gradient of the pressure here. Okay. And when I take the time average, I just get the gradient of the mean pressure alone. So, this is the additional contribution to the stress due to the turbulent velocity fluctuations. Okay. Note that it is an inertial term, it is minus rho times ui prime uj prime. So, it is effectively an inertial term. Okay. It is a convective transport of momentum due to the velocity fluctuations. Obviously, for example, if I take the shear stress component of this, I will get Txy is equal to minus rho times ux prime ui prime. Okay. If ux and ui prime, the fluctuating velocities are completely uncorrelated, this would be identically equal to 0. Okay. So, if they were independent variables, the Reynolds stress would be 0. The reason you have a Reynolds stress in a turbulent flow is because these velocities are actually correlated. Rather, they are anti-correlated. Okay. Clearly, only if ux prime ui prime is negative will the Reynolds stress be positive, okay, for this particular flow. Okay. So, what it implies is that a parcel of fluid going in the plus ux direction has a lower velocity ui than the average. A parcel of fluid going in the minus ux direction has a higher ui velocity than average. So, the idea is as follows: if I have a shear flow, okay, let us say I have a linear shear flow for simplicity. Okay. If it is a turbulent flow, okay, let us take a coordinate system here, x and y coordinate. If it is a turbulent flow, right, momentum is going to get transported, okay, from one location to the other, okay, only if a parcel of fluid going in the plus x direction, okay, I am sorry, a parcel of fluid going in the plus y direction, okay, has a negative ux component. So, that if a parcel of fluid over here has a velocity that is lower than average, when it goes up, okay, it is going to take its momentum deficit along with it, and it is going to get speeded up by the flow above. Okay. Whereas, a parcel of fluid coming down with a minus ui velocity will have a higher velocity ux. Okay. So, therefore, as it comes down, it will get slowed down, and therefore, it will transport momentum to the fluid that is below. Okay. If you recall, when we did our discussion of diffusion, molecular diffusion, the argument was exactly the same. Okay. We took a particular location across which there was a certain velocity profile, okay, and we said that molecules that are coming upward are coming on average one mean free path below the surface. Molecules that are going downwards are coming from on average a mean free path above the surface. Okay. And those molecules are the molecules coming downwards bring additional momentum with them, so to transfer it to the fluid below, whereas molecules going upwards take deficit of momentum with them to transfer it to the fluid above. Only then will you have momentum transport across the surface, resulting in a shear stress. Okay. So, this results in a shear stress if ux prime and ui prime are anti-correlated, okay, for a positive strain rate. Okay. So, what is it that generates these fluctuations, these fluctuating velocities, these highly irregular fluctuating velocities? Obviously, these fluctuating velocities have associated with them fluctuating strain rates. Okay. these fluctuating strain rates, these variations in velocities, are going to result in viscous dissipation. So, if I had a fluctuating velocity, viscous dissipation would tend to slow it down, unless for some reason there is a source of energy which is replenishing the energy of these fluctuating of these velocity fluctuations. So, we next looked at the mechanism by which velocity fluctuations are generated by writing down equations for the mean kinetic energy and the fluctuating kinetic energy. Okay. The mean kinetic energy per unit volume, okay, is of course equal to rho times, the mean kinetic energy is equal to half rho ui square, okay, and the kinetic energy of fluctuations is equal to half rho average of ui prime square, okay, the average of ui prime square. So, we tried to write an equation for the mean kinetic energy, and what we found was so that was the equation that we got in the previous lecture for the mean kinetic energy of the mean flow. Okay. These terms here, okay, the term on the left of course is the convected derivative of the turbulent kinetic energy, that is the rate at which the kinetic energy is transported. This is a steady state flow, so the time derivative is equal to 0. So, when the time derivative is equal to 0, the left hand side is just the convected derivative, because there is no time variation of half u square. Okay. In the right hand side, the three terms on the left are basically the divergence of something integrated, and if I were to write this for a volume, these three terms would be the divergence of something integrated over the fluid volume, which is basically the transport, the flux across the surface of the volume. So, this does not represent a net change in the energy of the fluid itself, but rather just the transport from one volume to the adjacent volume. Okay. The other three terms are actually what represent the net rate of change of energy. Okay. There should be a minus sign here, that is important. They represent the net change in the energy. Okay. The first one, the pressure times the divergence of the velocity, is the work done. In this case, if the flow is incompressible, that is identically equal to 0. Okay. If the flow is incompressible, that is the divergence of the velocity is equal to 0. The second term is the viscous dissipation, the viscous stress times the mean strain rate, the dissipation of energy due to the mean flow. Okay. So, this is the mean strain rate, this should be an average stress. Okay. This is the stress, this is not the fluctuating stress, but rather the average stress. Okay. So, this is an averaged equation. So, this represents the mean strain rate. Okay. The last term is the dissipation due to the Reynolds stress. Okay. So, this is not a viscous dissipation, it is a dissipation due to the fluctuating energy of the molecules. The viscous dissipation of course converts energy, mechanical energy into heat energy, into thermal energy, and increases the temperature. The Reynolds stress does not convert it into thermal energy, because it does not increase the fluctuating velocity of the molecules. It increases the fluid fluctuating velocity. So, it does not convert it into Reynolds stress, into heat, it does not convert it into heat. Okay. So, where does that energy go? The energy that is dissipated due to the Reynolds stress, where does that go? That basically increases the kinetic energy of the fluctuations. Okay. for this fluid, there is a kinetic energy of the fluid which is equal to half rho into u square, where u is the total fluid velocity. That kinetic energy we have separated into a kinetic energy for the mean flow, capital U square, plus a kinetic energy for the fluctuations, ui prime square. Okay. You can easily see that if I take the square of capital ui plus ui prime, the cross term 2 ui times ui prime averaged will be 0, because the average of ui prime is equal to 0. So, the kinetic energy separates out neatly into two parts, one due to the mean velocity and the other due to the velocity fluctuations. This dissipation term due to Reynolds stress is converting the energy from the mean flow kinetic energy to the kinetic energy of the velocity fluctuations. In other words, transferring energy from the mean flow to the fluctuations. As I said, because the dissipation in the stresses due to the Reynolds stress are much larger than that due to the molecular, the viscous stresses. Therefore, one would expect that this term, the Reynolds stress dissipation term, is actually much larger than the molecular, the viscous stress dissipation term, because as I said, in a turbulent flow, Tij Reynolds is much larger than the average of the molecular stress and the viscous stress. Okay. So, therefore, this is the dominant mechanism which is taking energy out of the mean flow. So, where does that energy go? Okay. In order to see that, one has to write a conservation equation for the kinetic energy of the fluctuations. Okay. I did not go through the details of the calculation in the last lecture, but just wrote down the final equation. It becomes rho uj partial by partial xj of half ui prime square. The fluctuating velocity is equal to okay. So, that was the energy for the turbulent kinetic energy fluctuations. The first terms that you see here are of course just the divergence of something, and if you write that down for a surface for a particular volume, this converts into a surface integral and just represents the exchange of energy between adjacent volumes. This term here appears with a negative sign, okay, the sign that is opposite to that in the mean kinetic energy equation. Okay. So, that acts as a transfer of energy from the mean flow to the fluctuations. Okay. So, this basically acts as the source term in the equation for the fluctuating kinetic energy, that is balanced by the dissipation due to the velocity fluctuations. Okay. So, this the source term, the Reynolds stress transfer of energy from the mean flow to the fluctuations, is balanced by the dissipation, the viscous dissipation due to the fluctuations. Okay. And this should be not a kinematic viscosity, but rather the dynamical viscosity itself. So, this acts as a transfer of energy to the fluctuations. So, energy is going from the mean flow to the fluctuations. The molecular viscous dissipation of energy in the mean flow equation is small. So, energy is going from the mean flow to the fluctuations, and in the equation for the fluctuating kinetic energy, this energy that is coming down from the mean flow is getting dissipated due to molecular due to viscous dissipation. So, that is the mechanism of dissipation in a turbulent flow. Because the viscous dissipation of the fluctuations is much larger than the viscous dissipation due to the mean flow, you get a friction coefficient or a drag coefficient which is much larger than what you would expect for a laminar flow in a turbulent velocity profile. So, next we looked at the question of where does the energy go. you have fluctuations across of course of various length scales, starting from the largest ones which are comparable to the system size, the channel width or the boundary layer thickness, for example. Then you have smaller and smaller eddies of various dimensions down to the smallest scales. So, what is the smallest scales of turbulence? Okay. The smallest scale of turbulence we had inferred on the basis of the Kolmogorov equilibrium, universal equilibrium hypothesis, as it is called. Okay. And the idea is as follows. Okay. For the smallest scales in a turbulent flow, it is assumed that the length and the time scales are much smaller than the largest flow scales. Okay. So, it is at the largest flow scales that the kinetic energy is getting pumped in from the mean flow to the fluctuations. Okay. So, let us, for definiteness, let us associate, for example, some length scale L and some velocity scale u to the largest scales. Okay. It is at the largest scales that energy is being pumped in to the fluctuations. Okay. What is the rate at which energy is being pumped into the fluctuations? Okay. As you know, on the left hand side in the equation for the mean kinetic energy, we had partial u I by partial x j. Okay. So, this will scale as rho u square into, I am sorry, in the kinetic energy equation we had this was partial by partial x j of half u I square. On the left hand side of the kinetic energy equation. Okay. So, this is the rate at which energy is coming in from the mean flow. Okay. This one can see is approximately equal to rho times u cubed by L. Okay. Usually, rather than writing the energy per unit volume, half rho u square is the energy per unit volume, it is more convenient to write it down in terms of the unit mass. Okay, because that reduces one mass dimension that we have to deal with. Okay, once we write in terms of the kinetic energy per unit mass, we no longer have to deal with the mass dimension. Okay. So, one can write the production of energy per unit mass rather than per unit volume by dividing it by the density. So, this is the rate at which there is production of energy, okay, u cubed by L. Okay. This has dimensions of length square t power minus 3. Okay. The rate of production of energy. This is the energy that goes down to the smallest eddies and gets dissipated. Okay. So, clearly this production rate of production of energy in a flow at steady state has got to be equal to the rate of dissipation of energy, okay, in the flow. Okay. Epsilon is called the rate of dissipation of energy. For the smallest scales themselves, okay, we assume that the length scale and the velocity scale are sufficiently small that they do not depend directly upon the macroscopic velocity scale u or the macroscopic length scale L, because if you have a region that is very small compared to the macroscopic scales, it is going to respond only to the local environment, not to the large spatial extent of the flow or the spatial or the macroscopic velocity. Okay. So, therefore, it depends only, it does not depend upon the macroscopic length scale L or the velocity scale u, but of course, it depends on those only through this rate of dissipation of energy epsilon, because this energy is ultimately going to have to be dissipated by these small scale flows. So, the length and the velocity scale do depend upon epsilon, but not independently on u or L. Okay. So, the smallest scales can depend upon epsilon. Okay. They could also depend upon the kinematic viscosity. Okay. They could also depend upon the kinematic viscosity nu, okay, with dimensions of length square T inverse. Okay. So, since the length and velocity scales of the smallest scale eddies depend only upon epsilon and nu, just from dimensional analysis, you can infer what the dependencies are. Okay. It is quite easy. Okay. Just from dimensional analysis, if I have to get a length scale from epsilon and nu, the only way that I can get a length scale is to write eta is equal to nu cubed by epsilon power 1/4. Okay. The velocity scale v for the smallest scales is nu epsilon power 1/4. Okay. And the time scale tau for the smallest scales is nu by epsilon power half. You can easily verify that these dependencies basically produce a length, a velocity and a time scale. Now, how do these compare to the macroscopic scales? Okay. Eta by L is equal to 1 by L into nu cubed by epsilon power 1/4. Okay. For epsilon, I can substitute u cubed by L, because I know that the production has got to be equal to the dissipation from here. Okay. So, for epsilon, I can substitute u cubed by L, and I will get nu cubed by u cubed L cubed power 1/4, okay, which is equal to the Reynolds number power minus 3 by 4. So, clearly the microscopic length scale is much smaller than the macroscopic scale. It goes as R e power minus 3/4. This is in the limit of high Reynolds number. Okay. So, clearly in the limit of high Reynolds number, this goes as R e power minus 3 by 4, which means that the smallest length scale is much larger than the macroscopic scale. Similarly, V by capital U, okay, that is the ratio of the smallest velocity scale to the large scale of flow, can be written as 1 over u times nu epsilon power 1 by 4th, okay, which goes as R e power minus 1/4. If you substitute epsilon is equal to u cubed by L, okay, if you substitute epsilon is equal to u cubed by L, you will get R e power minus 1/4. So, clearly the velocity scale of the smallest eddies is still much smaller than the velocity scale of the mean flow. Okay. So, these length and velocity scales are what are called the Kolmogorov scales. Okay, the smallest length and velocity scales in a turbulent flow. Okay. Even though both the length and the velocity scales in the smallest eddies are much smaller than those in the large scale flow, in the large scale flow, what about the strain rate? Okay. A scale for the strain rate for the small scale flow is approximately the smallest velocity divided by the Kolmogorov scale. Okay. There is a scale for the strain rate, okay, that is the gradient of the velocity field, the gradient of the velocity field at the smallest scales. Okay. And if you work this out, this will turn out to be equal to epsilon by nu per half. Okay. If I take the ratio of the strain rate for the smallest scales divided by the strain rate for the large scale flow, the strain rate for the smallest scales is V by eta. The strain rate for the large scale flow is equal to U by L. Okay. So, if I take the ratio of those two, okay, V by eta by U by L, okay, this is equal to epsilon by nu per half into L by U, okay, which if you substitute u cubed by L for epsilon, this turns out to be equal to Reynolds number plus half. Okay. So, even though the velocity scale is much smaller, the length scale is much smaller, the strain rate in the smallest eddies is actually much larger than the strain rate in the large scale flow. Okay. The strain rate in the smallest eddies is much larger than the strain rate in the large scale flow. Okay. So, this is the strain rate. How about the energy dissipation rate? Okay. The energy dissipation rate is proportional to the viscosity times the strain rate square. Okay. As I said, the rate of dissipation of energy is equal to shear stress times strain rate, which is equal to the viscosity times the strain rate square. Okay. So, the strain rate, ratio of strain rate in the small scale flow to the large scale flow is R e power plus half. That means the dissipation rate in the Kolmogorov scales divided by the dissipation rate in the mean flow is equal to R e power plus 1. Okay. It's equal to Reynolds number power plus 1 because it goes as a strain rate square. Okay. This is telling us something very important. When we wrote the equation for the mean kinetic energy or the mean momentum, we said that the inertial terms were order R e larger than the viscous terms. So, when we wrote the mean kinetic energy equation, the inertial terms and the production terms were R e larger than the viscous terms in the limit of high Reynolds number. Okay. And because of that, the dissipation due to the mean strain rate and the viscous dissipation due to the mean strain rate is smaller than the inertial terms in the kinetic energy equation. Inertial terms are R e larger than the viscous dissipation rate. What this is telling us is that the dissipation rate in the smallest scales is R e larger than the dissipation rate in the large scales. That means that the dissipation rate in the smallest scales is comparable to the inertial terms in the large scales. Okay. That is what determines the balance of energy. The flow itself creates smaller and smaller length scales until at the smallest length scale the dissipation rate balances the production rate in the largest macro scales. Okay. Because the dissipation rate balances the production rate, the flow is able to dissipate all the energy that is pumped into the macroscopic scales, into the larger scales. Okay. That is because it creates sufficiently small scales. Both the length and the velocity scales of the small scales are much smaller than the length and velocity scales of the large scale flow. The strain rate is much larger. It's sufficiently large to balance the production of energy in the mean flow. Okay. The dissipation due to the smallest scales is sufficient to balance the production of energy in the mean flow. Okay. And the other point is that I got a Reynolds number. Okay. I define the Reynolds number for the large scale as UL by the kinematic viscosity. Okay. I can similarly define a Reynolds number for the Kolmogorov scales as V eta by nu. Okay. I can also define a Reynolds number for the Kolmogorov scales as V eta by nu. Okay. And as we know, eta is given by nu cubed by epsilon power 1/4, okay, and V is given by nu epsilon power 1/4 by nu. This, as you can see, is equal to 1. Okay. So, it is creating sufficiently small scales. The Reynolds number based upon the large scale flow is large. However, the flow itself is creating smaller and smaller fluctuations at smaller and smaller scales, in such a way that for the smallest scales, inertial and viscous terms are comparable. The Reynolds number is order 1. Inertial and viscous terms are comparable, and because of that you have a balance between the production and the dissipation of energy at these smallest scales. Okay. The energy that is produced in the larger scales is dissipated at the smallest scales because the strain rate there is much larger than that in the large scales. Okay. So, you have what is called a cascade of energy in a turbulent flow. Okay. If I plot, for example, okay, as a function of the length scale, I have the large scale, the length scale of the flow. I have the large scale L corresponding to the macroscopic flow, and I have the small scale eta. Okay. Energy is coming in, being transferred from the mean flow to the fluctuations at this large scale L, as was shown by my mean kinetic energy equation, and that gets transferred to smaller and smaller scales, okay, until it is dissipated at this smallest Kolmogorov scale, at the scale where the Reynolds number becomes order 1, and therefore, there is a balance between the inertial and the viscous terms in the momentum conservation equation. There are other things that you can say about this kind of an energy transfer. Okay. The one thing is of course that energy is getting transferred from the large scale flow down to the small scale flow. Okay. We got the small scale just on the basis that at this smallest scale there is the scales themselves, the velocity, length and time scales do not depend upon the large scales, but only upon the rate of dissipation of energy and the kinematic viscosity. Okay. One can infer how the amount of energy in these flows varies. Okay. It is called the energy spectrum. Okay. The energy itself, the energy itself, the kinetic energy itself, I will call it as E here. This has units of length square T power minus 2. That is because I have scaled it by the density. Okay. So, this is energy per unit mass which has dimensions of length square T power minus 2. Okay. You know that in Fourier transforms you can always write this. Okay. The energy can be written as integral dk E of k. Okay. Where k goes from some small value to a large value. Okay. This k is equal to 2 pi by lambda, where lambda is equal to wavelength of fluctuations. Okay. You can take lambda as some characteristic eddy size. Okay. So, then E of k will give you the amount of energy in any eddies of that characteristic eddy size. Okay. So, the standard in Fourier analysis, if for those who are not familiar with this, kindly go back and refer to your notes on Fourier transforms. Okay. So, basically instead of writing down the size of the eddy itself, we write down the wavelength which is 2 pi by the size. Okay. So, this is a convenient way of expressing the spectrum. Okay. So, since k is equal to 2 pi by lambda, that means that if I write this in terms of k rather than in terms of the length scale, 2 pi by L will come down here. Okay, because it is 1 over L is much smaller than 1 over eta. Okay. Okay. So, you can easily see that since k has dimensions of length inverse, that means that E of k has to go as length cubed T power minus 2. Okay. Because energy has dimensions of length squared T power minus 2, k has dimensions of 1 over length, it is 2 pi by lambda. Okay. So, you can get some universal features of this E of k, the energy spectrum itself. Okay. For example, if you were at the smallest Kolmogorov scales, okay, just from dimensional analysis, the smallest energy scale has to go as is equal to length cube T power minus 2. Okay. This will go as nu power 5 by 4 epsilon power 1/4 times some function of k times eta. Okay. So, that is how you would expect the scaling to be at the smallest Kolmogorov scales, because the energy spectrum cannot depend upon u and L, it has to depend only upon nu and eta. Okay. So, that is at the smallest scales here, which corresponds to the largest value of k. Okay. So, at this end of the spectrum, which corresponds to the largest value of k, it has to scale, it has to be some function of nu cubed epsilon power minus nu power 5/4 epsilon power 1/4 times some function of eta. Okay. At the largest scales, of course, it has to scale only as u and L. Okay. So, this will basically turn out to be equal to u square L times some function of k times L. Okay. So, that is at the largest scales. Okay. It will scale in accordance with u and L. Okay. So, for this scale I have two limits here. Okay, let me just plot it again here as a function of k 2 pi by eta 2 pi by L E of k. Okay. At these two scales I know how it has to scale. It has to scale in some way as a function of k eta or k L depending upon the limit that you are taking. Okay. However, in the intermediate regime, when you are in between these two, okay, it cannot depend upon the kinematic viscosity either, because for the intermediate regime the kinematic viscosity is much smaller than the the viscous effects in the intermediate regime are negligible compared to inertial effects. Viscous and inertial effects become comparable only at the Kolmogorov scale. If you are in between the macroscopic scale and the Kolmogorov scale, there is an intermediate region where the small scale kinematic viscosity does not matter, as well as the large scale U and L do not matter. Okay. In this intermediate regime, the only thing that matters is the energy that is flowing through, the energy that is flowing through the entire system, epsilon itself. So, in this inertial subrange, as it is called, E of k depends only on epsilon and k. Okay. It cannot depend upon nu because the length scales are much larger than the Kolmogorov scales. It cannot depend upon U and L because the length scales are much smaller than the macroscopic scales. So, it can depend only upon epsilon and k. And just from dimensional analysis, you can easily see that in this intermediate regime, the energy just from dimensional analysis, it has to scale as E of k is equal to is rather proportional to epsilon power 2/3 k power minus 5/3. Okay. That is the only way you will get the correct dimensions, okay, epsilon power 2/3 k power minus 5/3. So, this predicts a scaling law for the energy in eddies of various intermediate sizes between the Kolmogorov scale and the macroscopic scale. Okay. So, what this is saying is that this energy spectrum has to have a minus 5/3 power. Okay. Okay. This I should state here. I am plotting log of k versus log of the energy. It has a minus 5/3 power, okay, as in the intermediate spectrum. Okay. So, what this is saying is that the energy in the macroscopic scale, the kinetic energy in the macroscopic scales is much larger than the kinetic energy in the Kolmogorov scales. Most of the energy is in the large scale flow. Okay. The energy in the small scale flow decreases as the eddy size decreases, with a scaling law which goes as k power minus 5/3 or length scale to the power plus 5/3. Okay. It decreases the length scale to the plus 5/3 power. Okay. In a manner similar to the energy spectrum, one can also get the dissipation spectrum. Okay. As I said, the dissipation of energy is proportional to mu into the strain rate square. Okay, which is proportional to mu times the velocity divided by the length scale whole square. Okay. And in my Fourier notation, I can write this as integral dk times d of k. Okay. So, basically the dissipation rate goes as 1 over the energy divided by length square. Okay. So, similarly the dissipation spectrum will also go as, will have dimensions of the energy spectrum will go as the energy spectrum divided by L square, which is proportional to L times t power minus 2, okay, just from dimensional analysis. And in the intermediate regime, this can depend only upon epsilon and k, and the only way it can depend upon that is as epsilon power 2/3 k power plus 1/3, okay, because it has dimensions of 1 over length square. So, that it is proportional to k square times the energy spectrum. Okay. So, in my figure that I had here, the dissipation spectrum actually increases as k power plus 1/3, okay, in the intermediate range. So, what this states is that the energy in the mean flow is much larger than the energy in the smallest scales, whereas the rate of dissipation of energy is largest for the smallest scales. Okay. K is equal to 2 pi by eta corresponds to the smallest scales of the flow, and the rate of dissipation of energy is largest for the smallest scales. Okay. So, this gives us a comprehensive idea of the flow energy, the length scales and the dissipation scales in the flow. Okay. How do you model these turbulent flows? Okay. The most commonly used model is what is called the K-Epsilon model, which is based upon what I had just done, the kinetic energy of the flow and the dissipation rate of the flow. It recognizes the fact that you have to have both kinetic energy and dissipation. Okay. Both of these have to be modeled. These could be inhomogeneous throughout the flow. You have to write additional equations for the kinetic energy and the dissipation rates. Okay. Here the shear stress, okay, is written as the turbulent viscosity times the strain rate. Okay. So, you write the shear stress tau ij is equal to, of course, there is the molecular viscosity plus there is a turbulent viscosity times grad u, in decimal notation is by partial xi. Okay. Where the turbulent viscosity is modeled as rho constant times the kinetic energy square divided by the rate of dissipation of energy. Okay. The kinetic energy goes as length square per time square and the dissipation of energy goes as length square per time cubed, and you can see that this combination basically it gives you a velocity times the length scale. Okay. Basically it gives you velocity times the length scale. Okay. The other models that are often used for this are what are called the mixing length models. The mixing length model is similar. Okay. It has some constant in it. It has a mixing length and it has a velocity of fluctuations. Okay. Rho times a diffusivity. Okay. Diffusivity has a length scale in it and a velocity scale in it, and u prime is the velocity of fluctuations, L is the length scale. Okay. And this velocity of fluctuations is often written as rho c mu times L square times the local gradient. Okay. The length scale times the local gradient gives you a velocity. Okay. So, these are what are called the mixing length models. Okay. Whereas, if you write in terms of the kinetic energy and the rate of dissipation of energy, it turns out to be the K epsilon model expression for the kinematic viscosity. So, this is the constitutive relation. Of course, to find the turbulent viscosity, I need to know what are K and epsilon, and typically equations are written for each of these. Okay. The left hand side for both of these are identical. There is a rate of change of kinetic energy and the rate of change of dissipation of energy. Both are substantial derivatives in a reference frame moving with the mean fluid velocity. Okay. Okay. In the right hand side for the kinetic energy, you have a diffusive term, basically the diffusion of kinetic energy due to inhomogeneities in the kinetic energy. Plus a production term minus the rate of dissipation of energy. Okay, so, this term is the production due to the mean flow, which I will come back to later. This the rate of dissipation of energy. Of course, if you are at steady state, a homogeneous flow, production would exactly balance dissipation. Okay. And in the equation for the dissipation of energy, I have a similar term here. Plus there is a term which is the production term, but it has to have an inverse time in it, because the rate of dissipation of energy is it does not have the same dimension as the kinetic energy itself. Epsilon has a dimension of 1 over t times k. That 1 over t is the turnover time which is taken into account by this epsilon by k over here. The turnover time which is taken into account by this epsilon by k, which has dimensions of 1 over t. Okay. So, that is the transfer of energy term from the mean kinetic energy to the fluctuations, and then I have a final dissipation term which goes as minus C2 epsilon times rho epsilon square by k. Okay. Once again, epsilon by k is 1 over time, it gives basically a turnover time, and epsilon divided by that time gives me the rate of change of epsilon. Okay. So, left hand side of both equations are the familiar convective derivative. On the right hand side, in both cases I have a diffusion term. The kinetic energy I have production, the inflow, the dissipation due to the kinetic energy, and in the dissipation term I have the mean flow energy transfer, and then I have a molecular energy dissipation term. Okay. Each of these are constants which are basically fitted. Okay. Each of these are constants which are basically fitted. Okay. All of these constants are fitted constants, okay, as well as the constant C mu here. Okay. The production is basically the mean kinetic energy production, okay, which is basically is equal to the turbulent mu plus mu t times partial ui by partial xj into which is equal to 2 mu plus mu t times the mean strain rate square. Okay. Note that this mu t here takes into account the fact that there is a Reynolds stress. So, there is the augmentation of the stress due to the Reynolds stress times the strain rate square. Okay. Basically gives me the production of energy, and that energy is dissipated. Okay. So, that is the balance between the production and dissipation is incorporated in these equations for the mean kinetic energy and the mean dissipation rate. Okay. And as I said, all of these are constants which have to be fitted. Okay. The common ones that I used based upon a large class of turbulent flows for these fitted constants are basically C mu in the equation for the viscosity is usually assumed as close to 0.09. Okay. This is the same whether it is a mixing length model or it is the K-Epsilon model. Okay. C1 epsilon is equal to 1.44, C2 epsilon is equal to 1.92, sigma k is actually very close to 1, okay, and sigma epsilon, okay, is taken as 1.3. Okay. So, these set of equations for k and epsilon basically give you what you need for the constitutive relation for the shear stress mu t for the mean velocity equation, mean momentum equation. These two coupled with the mean momentum equation basically form the K epsilon model for turbulent flows. Of course, there are various variations of this, okay. The K omega model and so on. You could have more constants depending upon whether you have buoyancy effects and other effects, and you could also take into account the vorticity equation and so on. But this is the one that is most commonly used, and basically it consists of an inertial a convective derivative of each of these quantities is equal to a diffusive part plus a production minus a dissipation. Put these in to calculate k and epsilon, use k and epsilon to get the kinematic the turbulent viscosity, and put that into the mean flow. Okay. So, I have taken this occasion to explain how the length scales of turbulent flow comes, what are the smallest and the largest length scales, and how the energy varies in between these two scales, and how elements of this energy transfer mechanism are taken into account in turbulence models for turbulent flows, which contain fitted constants of course, but they are broadly based upon the physical picture of the energy cascade for turbulent flows. In the next lecture, we will look at a concrete example of how we do modeling of turbulent flows, wall bounded turbulent flows, that is flows in a channel, which will be most useful for our case. So, we will continue with that discussion of turbulent flow in the next lecture. We will see you then.